So let's look at some small groups. So let's look at some finite groups that we know that have few elements. And let's look at groups with 4 elements. A group of order 4. So this just means G has 4 elements. That's what that means, right? The order of a group means the number of elements, but the order of an element is something else, right? That's the smallest power you have to take it to get to the identity. So I'm just talking about the number of elements in the group. Can you guys give me one? So this is something you should know for the test. What's a group of order 4?
C4.
Well, S4, the symmetric group is actually Z4. Okay, so that's what you meant here. Homework goes here. Thank you. Right, so Z4 is a good one. Of course, this is a nice group. What do you guys know about Z4? So it's got 4 elements. It's 0, 1, 2, 3. Can you tell me anything else about this? All right, so now you guys have various notions, various properties of groups that you want to ask yourself about. Anyone can tell me anything about this group? Is it?
Identity 0.
Okay, that's the identity. Good. And I mean, okay, and the inverse of 1 is 3, right? So everything has an inverse. You can write that down. In fact, we can write down the table, the multiplication table. So this is something you should be able to do on the test, right? So this one's easy. This is just modular arithmetic. Well, let me just do it this way. I guess what I was asking is it abelian? Right, that's one property we know. It's abelian. In fact, it's something stronger than abelian. It's cyclic, right? So this is a cyclic group because everything is a power of 1, right? It's actually also everything is a power of 3, right? So if you took all the powers of 3, you get 3 plus 3, which is 6, which is 2, 3 plus 2, which is 1, 1 plus 3 is 0. So you actually generate the whole group as well from 3. Remember this? It's a cyclic group with this as a generator or this as a generator. Okay, well, what's the multiplication table look like? It's this, right? It's well, always the identity row and column is easy, and then you just fill in the rest. So this is 1, 2, 3, 0, 3, 0, 1, 0. Is that right? Okay, right. That's the. That is completely the information of the group in some sense. Right? Okay, so this is a cyclic group, hence abelian. Remember, cyclic implies abelian. And again, remember abelian, you can read that off of the table because it's the symmetric matrix, right? It doesn't matter if you do 3 plus 2, you get 1. Or if you do 2 plus 3, you get 1. That's it's a symmetric matrix. Okay. Can you guys give me another group of order 4? So we've seen at least one other one.
Z2 cross Z2.
Okay, great. Z2 cross Z2. Now remember, this guy has elements. Again, this is something I want you to be able to tell me something about. So what are the elements here? Well, they're ordered pairs, where the first entry is 0, 1, and the second entry is 0, 1. So what does that look like? It's 0, 0, 0, 1, 1, 0, and 1, 1. Well, this guy's also abelian, right? Because you guys proved on your homework, if you have two groups that are abelian, you take the product, you get an abelian group. So this is also abelian. Is it cyclic? So is there an element that generates everything? Is there an element that you can take whose powers give you everything? No, right? You can always, for small examples, just check it, right? So this guy's not going to work, that's the identity. If you take this guy and you start adding to itself, well, you get nowhere fast, right? You take 0, 1 plus 0, 1, you get this. So it has order 2, right? This element has order 2. What about this guy? Order 2, right? Because 1, 0 plus 1, 0 is the identity. And same with this guy. All the non-identity elements, this is not cyclic, in fact, all non-identity elements have order 2. So let's make the table for this guy, because they're small, we can do this. Okay, so now I've got 0, 0, 0, 1, 1, 0, 1, 1. Let's go through the whole thing, because I think this is useful. Okay, so maybe I could have called these different things, but okay. So again, this is the identity. Right? When you have a product of groups, the identity is going to be the element that has the identity in each component. Right? So I mean, this is the 0 is the identity of Z2, and the 0 is the identity of Z2. So that pair will be the identity of the product. So again, first row, first column is easy. You just copy down what you saw above it, or beside it. 0, 1, 1, 0. And now what about this row? So what's 0, 1 plus 0, 1? Well, you just told me. Right? In fact, we know the diagonal of this guy. Right? Because everything has order 2 or less, it means that the diagonal is going to be the identity of it. Right? 1, 1 plus 1, 1. And then let's fill in the rest. So this is what? 1, 1. What goes here? 1, 0. Bless you. This is also a symmetric thing, so I only have to do this one, and then I'm, in some sense, done. So I can just transpose everything. What's that? 0, 1. Okay, so this is what? 1, 1. 1, 0. And then this is 0, 1. Okay, so again, that's all the information of the group. And for these small examples, we can actually write this down, and but you can imagine that once a group has maybe 10 elements, you don't really want to do this anymore. I mean, somehow it's not the right way to think about the group. But I'm going to do it one more time, because there was another group of order 4 that we saw, and this is going to tie us into this isomorphism business. So if you remember from, I forgot which homework this was now, you just gave me, did I already lose the page you gave me? It's here somewhere, I'll find it, I promise.
I have another copy of it.
Oh, well that's okay, it's actually not from this homework that can I see? So do you guys remember we were looking at a certain subgroup of S4, okay there it is, that's the one, yeah. From homework number 3. So do you remember this optional problem number 9 from homework number 3? Homework number 3, question 9. You looked at a certain subgroup of S4. So I'm going to call it V, because it's usually called V. Well, I'm going to use our notation that we have now. So epsilon 1, 2, 3, 4, this is an element of S4. 1, 3, 2, 4, this is an element of S4. 1, 4, 2, 3. Actually, that's all I guess I need here. So this is a subset of S4, right? Because you guys comfortable with this notation, right? These are cycles. This is a cycle decomposition of an element in S4, right? So this guy is really the permutation that sends, well, what? Sends 1 to 2, 2 to 1, 3 to 4. Okay. So again, I don't like this notation. It's cumbersome. We like this notation, the disjoint cycle notation. Okay. Now on this homework, well, one question I think was to show that this is actually a group, that this is a subgroup of S4, right? It's, by definition, it's a subset. I gave you some elements, right? But it turns out this actually forms a little subgroup of order 4, which means itself, in its own right, is a group. So this is called the, Klein group of order 4, right? It has 4 elements. It's a subgroup of S4. Now remember, when you have a subgroup of something, that means it itself is a group. So this is a group. Let's make the multiplication table. Okay, so let's see if it resembles any of either of these groups here. I mean, I should have said that, here's 2 groups before we talk about that. Here's 2 groups that have 4 elements. They are different, right? I mean, somehow they don't feel the same because, this is a cyclic group, right? I mean, this has an element 1 whose powers, generate the group. So 1 squared is 2, 1 cubed is 3. Whereas this guy has all the elements that square to the identity. So if you take any element and you add it to itself, you get the identity. So we're going to make this more precise in a second, but somehow we should feel that these are different. Okay? Now what about this guy? This seems totally different than all of those because it's about permutations. But let's see what happens. So if I make the multiplication table, let's see, now I will give these some names just to make my life easier. I don't have any colors. So let me call this maybe alpha. I think that's what I called it in the homework. This is beta, this is gamma. So let's see, you guys help me out here. So we've got the multiplication table. So now this is composition is my operation, right? Because these are permutations. Yeah, maybe I should have said here this was plus. It's almost like plus comma plus, right? Because I'm doing the operations coordinate-wise. But it's the operation of the product. This is composition. So what's going on here? If I epsilon alpha beta gamma, whoops, epsilon alpha beta gamma. Well, again, the first row and column we know what's going on. Okay, well let's see. What happens with alpha times alpha? So I've run out of board space here, but let's do a little side calculation. If I take alpha composed with alpha, that's the same thing as taking this guy times itself. So that's 1, 2, 3, 4 times 1, 2, 3, 4. Now we could go through and say where does 1 go and blah, 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 but notice that these are disjoint cycles, so I can pass them through each other, right? If you have cycles that don't share elements, they commute. Remember this stuff? So this is actually the same as 1, 2 times 1, 2 times 3, 4 times 3, 4. But be careful, you can only do that with permutations that are disjoint. Otherwise, you can't just flip order. Now what happens if I send 3 to 4 and 4 to 3, and then send 3 to 4 and 4 to 3? I mean, this is the identity, right? If you take a transposition times itself, it's the identity. And then same here, right? So this is just identity times identity. So what do you get? Identity. That make sense? And again, you could draw out the whole permutation, 2-line notation if you like, but I don't want you to do that. I want you to realize that we've got cycle notation, they're disjoint, so when I can use these tools now, I can make my life easier. Okay, so this is alpha. Well, can you see what's going to happen with beta times beta? Same deal, right? Bless you, right? If I take beta times beta, same situation, I've just got the 1, 3, 2, 4 now. So what's beta times beta? Identity. Look at gamma, that's the same thing, right? It's a 2-cycle times a disjoint 2-cycle. So I've got another gamma squared is the identity. Okay? Well, let's do one of these calculations, but I think, it's a little tedious, but let me just go through. Maybe we'll do beta times alpha. So beta times alpha is really beta composed with alpha, which is really, what was beta? 1, 3, 2, 4 times alpha, which is 1, 2, 3, 4. Okay, now I can't really, I can move this over. I could flip these two, but then it won't be disjoint, so I can't really make my life easier anymore. I can't do the same trick, so let's actually go through the calculation, because you will have to do that on Thursday. Okay, so let's do it. Where does 1 go? So it's not touched by this guy. It gets sent to 2, which then goes to 4, and then it's not touched. So 1 goes to 4. Where does 4 go? Well, 4 goes to 3, not touched, then goes to 1. Okay. What is the smallest thing I haven't considered yet is 2. 2 is not touched by this guy. 2 goes to 1, which goes to 3. Where does 3 go? To 4, to 2, not touched. So what's that one? 1, 4, 2, 3 is gamma. Okay, so this is gamma. And can you guess what this has to be actually? Right, in any row of a multiplication table, you have to have every element appear exactly once. So this has to be what? This has to be beta looking weird. Let's see, is this right? And this is alpha. Yeah, okay, that looks good. Oh, I just didn't do a row, that's why it looks weird. I haven't done this row. So what is alpha times beta? It's going to be gamma, I'll tell you that. I mean, again, it's almost Sudoku again, right? Because it has to be the thing you haven't seen here. And then what is this guy? Beta. This is how you make a multiplication table, right? So it's already tedious for your 4 elements. But here's the punchline. I mean, this is a bunch of permutation. Well, first of all, the punchline is that it is a group. This actually proves it's a group. Because, I mean, assuming you believe all my calculations, because you know that there's an identity. You know that the inverse of alpha is itself. The inverse of beta is itself. The inverse of gamma is itself, right? That's what you need for a group. You need an identity, and you need every element to have an inverse. So this table certifies that, and that's what. And of course, the associativity comes because everything is composition, which we know is associative. Okay, but the other punchline I want to emphasize here is that this table looks a lot like this table. And what I mean by that is I can relabel elements here with the epsilon, alpha, beta, gamma so that it actually looks exactly like this table. So what I mean by that is if I call this guy, so I wish I had another color. So can you guys see if you take those elements of the Z2 cross Z2 and actually relabel them, I've got whiteboard pens, so that's not going to work. They're colored though. Okay, so, well, this one's easy, right? If I want to make this table look like that, I know what the identity has to be. It has to be an epsilon, right? Now, well, let's see. So, is it enough to just call it what it is? I mean, so if I call this alpha, right, and this beta, and this gamma, I'm not really crossing it out, right? I'm relabeling. So that means this one becomes alpha, beta, gamma. Then what happens is that this table actually coincides exactly with this, right? So for instance, you know, what happened to beta times beta? Well, we knew that that was epsilon. That was the identity. What happens to, say, beta times alpha? Well, that's the same as gamma. And look at this. Beta times alpha is gamma. So what we've done here is we've made it what's going to be called an isomorphism between the group Z2 cross Z2 and this guy, the Klein group. Okay, and so this is going to be the notion. I mean, we're going to sort of make this more precise as we go, but that's the idea, is that these two groups are the same up to relabeling the elements. Okay, so I'll just say so we can see that Z2 cross Z2 and this V guy determine the same multiplication table. After we relabel, right? Now, of course, I kind of got lucky that I put my things in the right order so that my relabeling was easy. But in general, there's going to be what? Well, I guess the identity always has to be the identity. But in general, there's going to be sort of n factorial ways to possibly relabel, and you won't always get so lucky. I mean, in these small things, you can sort of see how it works. But this is going to be a more complicated question in general. But here's the definition that we're going to. So let's let G1 and G2 be groups. Okay, so here's the definition. A bijective function, right, that's a relabeling, f from G1 to G2, such that f of A star B equals f of A star f of B. So we have to have a bijective function with an extra property. This is called an isomorphism. Okay, so let me just make a couple comments here. Notice that, F is moving G1 to G2. So maybe I can just draw this picture here. Here's G1, here's G2. So F is the guy that moves elements from one to the other, right? And if I'm inputting something into the function, it has to happen, this has to be an element of G1. So what's happening is I'm taking A star B over here. This A star B is an element of G1, right? Because it's something in G1 times something in G2. And I send it over. It has to be the same as, taking F of A star F of B. So this guy, has to be, so these operations, be careful, they're happening, this is happening in G1, this is happening in G2. But what this formula is saying is that it's preserving the operations, right? It's taking the operation of one world into the operation of the other world in this coherent way, in the way that preserves the structure. Okay? So it's it's not just a bijection, because we saw that with Z4, maybe I should have right, so what I'm trying to say here is that this labeling that we just wrote down is such a thing. So maybe I can just say that what we did above. So an example of an isomorphism is given above, where I took, what was this? This was Z2 cross Z2, and I mapped it over to V. How do I define a function? Well, you have to tell me what to do to the elements of Z2 cross Z2, right? So, F of 0, 0 was E. F of 0, 1 was alpha. F of 1, 0 was beta. And F of 1, 1 was gamma. Right? When it comes down to it, a function is just something that assigns an element of one guy to the other guy. Now, to check this other condition, well, that would require some work, but that's what this table is doing for us. So we'll do some more examples in a second, but this is really what's going on. This is the idea. Okay, so questions about that is that, that's the definition. We're going to now do some more examples. I should give you one more definition here. So if there exists an isomorphism from G1 to G2, we say that G1 and G2 are isomorphic. Okay, so this is, again, this is very typical in math. You guys have taken a bunch of math classes. Especially in the algebraic setting, when you're dealing with something that has some structure, right? You want to define the object, and then you want to define what does it mean for two guys to be the same, right? Up to the structure that we're studying. So, in some sense, this group, a priori, it lives in a different world. It consists of permutations. But it's really the same as far as the algebra is concerned. It's the same as Z2 cross Z2. Okay, so they're isomorphic groups. Maybe I should just say that, why is it the case that, I'll say this later, but, to show that something's not isomorphic is a little bit harder because you have to show that there does not exist such a function. So we'll talk about some sort of techniques for saying that. What else I want to say? Questions about this? So isomorphism is that definition. It's a bijective function that preserves the operations on both sides. So, maybe the comments I want to make is sort of two things. how do you, if you give me two groups now, how do you show they're isomorphic? And then if you give me two groups, how do you show they're not isomorphic? And what are the sort of techniques for both of those? So given two groups, G1 and G2, I won't say too much about this because this is kind of where we'll go after the test a little bit. But to verify, I should also say, we say that G1 and G2 are isomorphic, and we write, the usual notation for this is G1, and then this equal sign with the tilde on top, G2, that's isomorphic. Again, that's kind of typical for whatever objects you're talking about. This is kind of your isomorphic symbol. So to verify that G1 and G2 are isomorphic, so in some sense it's easy because you just, here's the definition, right? You need to find this thing. So a priori it's kind of an easy thing. You must find a bijection satisfying the property. And I'll put this as star. So somehow your goal is right there in front of you. It's telling you what to do. But on the other hand, if G1 and G2 are, if they have many elements or if they're infinite, then it's not going to be so easy. So just randomly trying functions is not going to work. So how do you find a bijection satisfying this? Well, then there's some art to it. I'll give you an example. One way is to guess the function. So maybe, I can't answer this, there's no sort of formula that always works. This is what we have to do. We have to find the bijection. So maybe first, guess a bijection and check star. Let me give you an example of this. So one that you guys know and love is kind of famous isomorphism. I'll leave that one on the board because that's the main definition. So here's an example. The G1 is, let's say, the real numbers with addition, and G2 is the positive real numbers. So that's what that means, the positive real numbers under multiplication. All right, those are groups, right? Of course, the real numbers are under addition is a group with 0 as the identity. The positive real numbers are a group with 1 as the identity. With multiplication, is 1 as the identity. The inverse of 6 is 1/6. The inverse of pi is 1 over pi. Are these isomorphic? So I claim G1 is isomorphic to G2. Okay, so again, to verify that, we need to find a bijection. So do you guys know a way to take a real number into a positive real number? Okay, lots of ways to do that. But we want one that preserves we want one that takes addition into multiplication. Okay, great. Exponentiation, right? So let's let f of x, let's define a function. F from G1 to G2 by, so f of x will be e to the x. This is for any x real number. Okay, so it definitely maps to the positive real numbers, right? The x, e to anything is non-negative. It's actually positive, right? And so this is a bijection. So this is a bijection. Right? Every positive real number is of the form e to something, and it's 1 to 1, right? The graph of e to the x passes the horizontal line test, right? Okay, so it takes it takes all the real numbers onto the positive real numbers. Okay? Now, does it satisfy the property? Okay, so it's bijective, and, well, we need to check that f of, well, let's see, so the star needs to be equal to f of x star f of y. In other words, so what's the star on the left-hand side? Plus, right? So is it true that f of x plus y equals f of x times f of y? Well, what is f? Yeah, this is the same as e to the x plus y equals e to the x times e to the y. Look at that. That's your rule of exponents. Yeah, so you really maybe want to go the other way when you prove this, right? And this is something you know from your rules of exponents, and what that's really saying in this context is that the condition is satisfied. So conclusion, it is they are isomorphic, right? That's weird. I mean, the group of real numbers under addition is the same in the in terms of group theory as the positive real numbers under multiplication. Of course, if you guys wanted to make the map G2 to G1, what would it be? Logarithm, right? So the way to take multiplication to addition is the log. Okay, so these isomorphisms you've seen before. Let me just say, and then maybe we can break. The other comment is, how do you show that something's not, if you give me two groups, how do you determine if they're not isomorphic? Okay, so the other bullet point was how to recognize that G1 and G2 are not isomorphic. Well, this is harder in some sense, right? Because, well, I have to say that there does not exist one of these. Well, so again, I could go through all the list. If it was a finite group, then I could actually check them all. But that's not going to be your, I mean, that would take forever, even if it was 4 elements. So this, again, I don't have a good answer for. We're going to build up some techniques. The easiest way to tell that there's not a bijective function, I mean, if we're just, forget about the group theory, this needs to be a bijection between two things. So the easiest thing to look for is if they have different number of elements, right? I mean, so if G1 and G2 have different cardinalities, they cannot be isomorphic. Right, so this is all in the answering the question of not isomorphic. If one guy has 10 elements, the other guy has 20, then it can't be isomorphic. There's no bijection. And then, well, then you look at these various properties. Maybe the abelianness. So one other thing you do is if G1 is abelian, but G2 is not. That's an easy check because usually here's two groups, usually you can sort of see or you know something about the group. One is abelian, one's not, then you can immediately rule out that they're isomorphic. Maybe G1 is cyclic. G2 is not. And then the last thing I'll say is the orders of elements. You can consider the orders of elements now. Okay, so this was the order of the groups themselves, right? If the size of the groups are different, then they can't be isomorphic. But then you can sort of dig deeper and look at what are the orders of elements. Maybe G1 has an element of order 2, whereas G2 does not. Something like that. So I'll just leave it there. I mean, we'll see examples of this. But just maybe as a last comment, then we'll break. So for instance, is S6 isomorphic to S3, symmetric group on 3 letters. Is that isomorphic to Z6? Well, they have the same number of elements, right? So both, how many elements do they have? Both groups have 6 elements. So the easy kind of thing is out the window. But the next thing is not, right? So what's the next check? I mean, again, these are not, I'm not numbering these items, these are just things to keep in mind. Well, Z6 is cyclic, hence abelian. This symmetric group is not, right? S3 is not abelian. So S3 is not abelian. But Z6 is abelian. So hence they cannot be isomorphic. Okay, so these are legitimately different groups. The set of permutations of 3 elements, which consists of 6 things, is a group that's not at all like Z6. They're different. They're not. The group theory can see the difference. Okay, so maybe we'll break till 25, and then I've got some more discussion